So again, this is a grand potential implementation we have done in OpenFOAM. And so you'll need a few things. So OpenFOAM in box, it's a package which CFT support team has developed, which will take care of all. So similar to Singularity, where you don't have to Singularity images, where you don't have to install any of this stuff, just load the Singularity image and all the essential prerequisite softwares and packages which are required, they will be loaded. So similarly for OpenFOAM also, there is something called as OpenFOAM in box. So we have tested our solvers on OpenFOAM in box 20 and OpenFOAM in box 18. So OpenFOAM in box 20 is based on openfoam.org version 8. Okay. So again, I have shared this particular installation file with you. So if you go to GP OpenFOAM, you can see the OpenFOAM in box 20 .sh file. Once you have this particular file, okay, so you can download the file. After that, I can show these things. I have already, but I have already installed on my system.
But you don't need to reinstall.
Yeah.
You just show them.
Yeah. Yeah. Okay. Okay, you can do one thing. Okay, I think I don't have this final sh file, but all you have to do is just go to the terminal. By default, if you open the terminal, you'll be in home. Okay. So from this place, okay, this becomes. From here itself, you can do mkdir -p. So I mean, we have written, so we have given this ~/ so that means automatically it will create a folder in the home, even if you are not in the home folder. And then OpenFOAM inbox. So I have, since it's already created, it will not do anything. So then you can navigate to OpenFOAM and OpenFOAM inbox. Okay. So you're supposed to copy this sh file to this particular location. So at the moment, I don't have it here. And after that, just run this particular command. So in this particular folder, OpenFOAM inbox, you need to have the sh file. Once you click on run this command, bash openfoam.sh install, it will generate this particular folder, OpenFOAM inbox 20 and so forth. Okay, and once you have installed this, so is there anyone who is trying this here? Does anyone have the OpenFOAM sh file? Okay, fine. Then I can just quickly run through if no one is trying out here. And after that, there are some environment variables which needs to be loaded after you. So whenever you want to use OpenFOAM. So that's why in this particular command, echo source, I think I'll increase the font a little bit. Yeah. So in this particular command, echo source, and so a bash RC file is located in the OpenFOAM inbox installation, which will source all the environment variable. For example, we need to use certain commands to compile and to run our simulations. So all of those will be loaded, and we are putting that into the system's bash RC file, and then we just source the bash RC file. So in my case, I can show you that. So I have opened the bash RC file of Ubuntu, and in the end, you can see that you will, after you run this particular command, echo source, you should see something like this. Okay, and this particular file .bashrc, this is sourced every time you open a new terminal. Okay, so since we have sourced it, you can run any of the OpenFOAM commands. For example, user. So this is a generic OpenFOAM command where I want to see where my solvers. So when we have solvers, so when we compile those solvers, the executable goes to a particular location. So that location we can find by using this foam user app bin. So if suppose this kind of commands are working, that means your installation is done properly and you have sourced the OpenFOAM bash RC as well. So I can do one more thing. Okay. Oops. Okay, so if I check the foam app bin, so right now I listed all of the executables which are present in foam app bin. So these are not the user executable, these are there as a part of the OpenFOAM package. So in the user, I only have the face field, so which is our solver, which I have already compiled, so I can see it here. When you run that for the first time, you won't see anything here. But all these green colored files that you see, those are the inbuilt solvers which are present in OpenFOAM. Okay. So once that is done, there is just one more dependency that is required to run our solver, which is the GSL library. So we are doing some spline interpolations in our solver, so for which we need this particular file. Okay. This mkdir -p foam run, even if you don't run this command, it should be still fine. But as a fallback, it's written here. And next is the GSL command. So it's simple sudo apt install libgsl dev. This will install the GSL library, and we have made provisions properly in the solvers so that it will automatically, if you install it at the default location, our solver can detect all of the libraries, GSL libraries, which you have installed, and it will take those libraries and use them for the compilation and the execution. And then we can use paraview gnu plot. Those things are there. So with this OpenFOAM, you also get a paraview inbuilt into it. See, by default, it has a paraview 5.8 as well. So once this installation, so this is all that is required in terms of the installation for the OpenFOAM solvers. So any questions here? Okay, questions, I'll check. Okay, yeah. So next, you need to navigate to the folder where the solver and the case files are stored. I'll tell you what those things are. Okay. Now before we go into the details of this, what we'll do. So we just want to go through what is our development in the OpenFOAM. So some of the previous development and the new development that has been done in the past 1 year. Okay. So since past 1 year, all the developments that have been made in terms of precipitation and then 3D solidification solutions. So those were done by Tanmay, but since he's sick, he's not able to join here. So I'll try my best to try to explain and present his work. Along with me, Professor Abhik will also assist. Yeah. Okay. So this is from our previous development. So as as we saw in the all the previous sessions, it's a typical phase filled formulation where you have the square gradient term, and then you have a double well potential or an obstacle potential, and then you have the driving force. So here the driving force comes from the grand potential, and the extra addition which is there in this particular formulation is the orientation field, where instead of, so as you saw in the multi-phase field models which were discussed previously, there you have, if you have n number of phases, you'll have n number of order parameters phi n, which would describe different phases or different orientations of grains. So if you have a multi-grain simulation where you have grains with different orientations, so they can be represented with different order parameters. So instead of that, in this formulation, we just have one particular order parameter phi, which will represent whether it is a solid or liquid or an interface. And then there is another order parameter, which is theta, which will tell us a particular solid that is there, what is its crystallographic orientation. Okay. So this simplifies the problem when we want to uh, run the simulations for large number of grains which have n number of orientations. So all of that can be taken care by solving just one extra equation instead of solving n number of phase field equations. And I think I can skip this part. So these are the evolution equations. We have the phase field evolution equation, and this is the theta evolution equation. And then I think this similar type of equation was showed earlier, this which is a chemical potential equation, chemical potential evolution equation. So this is a simulation for binary alloy grain growth problem, where we are, so on the left hand side here, red colored structures that you see, those are the solids, blue color is the liquid, and on the right hand side the different colors that you see, those are different grains. So this is the right hand side field is the theta field, and different colors are different orientations of the grains. So here we have incorporated the, or Tanmay has coupled the thermodynamic database, and so that we can take a binary system, also ternary system as well, which I'll show in the next slides. So we can take the thermodynamic properties of the, let's say here the ALZN alloy, and as it was coupled previously also that you saw from the thermodynamic databases, encrypted and encrypted, you can get the Hessians and the compositions, etc. And those can be used for this particular simulations. So here, in this particular simulation, we nucleate the random grains with the nucleation probability, which is based on, again, the undercooling. So based on undercooling, a certain number of nucleation probability will be there. And we get this kind of simulations. So if we give a certain cooling rate, so if you have a casting simulation where you are extracting heat at a certain rate, and if you run our OpenFOAM phase field simulations, you can reproduce the cooling curves which you experimentally observe. And here, this is with respect to time. If you plot the temperature in the domain, this is the curve that you'll get. And here it is dropping suddenly, and then you see a flattening here, which is happening because of the because some solidification is happening. And then as the solid volume fraction increases, there will be a latent heat which would be evolved. So latent heat is given out from the solid to the liquid region, which would increase the temperature of the system. So that's why there is cooling as well as heating happening, because of which you see some flattening. And then after a certain volume fraction, again, you see a dip in the temperature. And this is the temperature rate evolution as a function of time. Then here we have compared the OpenFOAM simulation Uh, so the liquidus composition as it varies. Yeah, so the liquid composition from the simulation compared with the Scheil calculation. Okay, so these are the plots. You want to add something?
No. So that's essentially one of the Scheil calculation is pretty basic that you typically do from thermodynamic softwares, and that has certain assumptions in it. And what this software allows you, this calculation allows you to do is to make a dynamic prediction. Prediction from a dynamical simulation. So the blue curve over there essentially is a estimate from a dynamical simulation. And you can see that the estimates are fairly consistent with what the Scheil is, as you expect, but there are certain important differences, particularly with how it approaches the uh, zero liquid fraction, and those are relevant for the final compositions during the last stage of solidification, which might be relevant for the future precipitates or future phases might form that might form post solidification. So those differences might become important, and therefore it's important to highlight them in contrast to what you get initially.
So this is the ternary simulation where we are taking the thermodynamic properties of nickel, aluminum, molybdenum alloy, and you can see that we can simulate grain growth in ternary systems as well. Again, here we have done similar things, randomly nucleate based on the nucleation probability, and we are giving some undercooling. And so these are the at the end we see this kind of structures. Then again, we have temperature evolution and temperature rate evolutions. And so this is about, so now there are two major additions. So these things were there in the previous version. So the new additions are 3D. You can do now 3D simulations as well as the precipitation and along with the incorporation of elasticity effects. So
So essentially, this is what I had given an overview during my talk in the first session. So as you saw in the formulation before, particularly if you just go to the first slide over here, that you have a gradient theta, which is theta is the uniform or a continuous orientation field, which is essentially showing you how the orientation is distributed in the domain that you're solving for. So theta is a function. So one theta field suffices in 2D because you have just one way to rotate, and therefore one rotation field suffices. As soon as you go into a 3D formulation, you will need three different Euler angles to describe the orientation. So in principle, your field cannot remain scalar like this. It needs to become a vector field. So typically, you would like to have a field which is representing the different orientations in space. So one very useful transformation here is utilizing quaternions, because rotations in the quaternion space become just algebraic operations. So you can represent orientations in the quaternion space as a 4-element vector, where the 3 elements represent the Euler angles and one of them represents the magnitude. So that allows you to do so for example, this is a uh, example of a 4-component vector that represents a particular orientation. It's a 4D vector space, and essentially this q1, q2, q3 represents the orientation precisely, and q0 is the scalar or the real part of the thing. So this essentially is a complex number. You have q0 plus iq1 plus jq2 plus kq3. That's essentially the quaternion. Now, why we write it like this is because when you want to rotate a particular orientation into another one, in actuality, that rotation is a very, very complicated operation and computationally intensive operation. However, in the quaternion space, it becomes an algebraic operation, which makes it very convenient to use. Okay, so this is all standard transformations, how you get from a particular orientation, how you retrieve back these components. And one of the major things that is required is that you need to have this constraint, that is the summation of qi squared, that are these components, should yield 1. This is because the orientation is a fixed quantity. It must rotate on the sphere with of a fixed magnitude. You cannot have the magnitude changing. So you need to evaluate or have the time integration scheme in a way that your magnitude of the orientation field does not change. Doesn't make sense physically in way. So that is what this takes care of. And so there are different notations of how you rotate about x, y, z, which are the typical rotations, and you can create these matrices, this quaternion vectors. And once you have done that, this is how your q0, q1, q2 would look like for arbitrary theta x, theta y, theta z rotation orientation. Okay, so this is actually there in the OpenFOAM library as a quaternion library, so you can utilize all of those functions directly. So going from the Euler space to the quaternion space and back is already there, right? Because I think it was used somewhere in the OpenFOAM library itself. So because of that, it will become very rather trivial uh, to do these transformations to and fro from the Euler to the thing and back after rotating, because rotations are required when we do the phase field equations. When you want to describe anisotropy, you saw dendrites which were oriented in a particular angle. So that required a rotation of the anisotropy, rotation of the surface energy formulation, which is a function of a normal vector. Now those rotations are done by rotation matrices and operations of rotations. Now that same thing we will be doing using quaternions over here, right? So that's essentially what the thing is. So from the original formulation, what changes is precisely that from gradient theta, you become gradient qi, and it's a summation over all qi. And because it's now like this, your you see over here, it becomes a summation over all I, grad qi. But because of the constraint that summation qi squared is yielding 1, you need to integrate using a Lagrange parameter in your theta equation, which comes over here. That ensures that your integration remains with the constraint summation qi squared. So that's in principle the only change. So the Lagrange parameter you can evaluate, it has to be this much for that particular constraint, and then the original equation remains the same. So now you are solving for a phi dot equation and 3 q naught q0, q1, q2, q3, 4 components of the orientation quaternion space vector, along with any number of components that you are solving for. For a ternary, it will be mu1 and mu2. Okay, so number of equations have gone up, but not to the extent that you would typically have in a multi-order parameter multi-phase field model. Okay, that's the advantage. Okay.
So as I was saying, along with this, we have a 3D simulation that we have that Tanmay has added in the model now. So as you can see here, we see a 3D simulation of 250 cross 250 cross 250 domain, where I think this red is the solid region and the hollow space that you see, that should be liquid. And this is again done with the thermodynamic coupling for a ALZN system. And these are the Euler angles. So this is the theta x angle. So we have 3 Euler angles, theta x. Here we have theta y and theta z. Okay. And I think rest of the things I covered.
Yeah. So along with this, precipitation is also included in this. So the elastic component is also part of the solver. So OpenFOAM therefore offers you binary, ternary, solidification, precipitation, inclusion of elasticity. These 5 capabilities that come.
So we'll move on to the demonstration of all these things that we saw. So we won't be able to show any 3D simulations because it's not feasible to do it on my laptop. But I'll show you how to run some of the simulations, and we'll visualize some of the 2D cases, binary as well as the ternary ones.
So the motivation to go for OpenFOAM, just to add to what he's saying, is essentially to access some of the implicit solvers that come as a package with OpenFOAM. OpenFOAM is a multiphysics library, and it comes with these multiphysics solver modules as well as nonlinear linear algebra libraries. So we wanted to access them, and therefore some of these modules we have added as part of the OpenFOAM. So anybody who has OpenFOAM, you can just install OpenFOAM in your computer and essentially put these modules there, and you will be able to run them. So and access these powerful linear algebra libraries.
So as I already walked you through the installation. So we'll come to the actual compilation and then running the simulations. So you can download all of this case files and the OpenFOAM solver from our GitHub library, GitHub repository. So the organization of OpenFOAM is something like this. So they call solver. So whatever you saw, the formulation, all of that, that goes into the solver part. And then all of the case setup, for example, how your mesh will look like, what all input parameters, what transport properties, thermodynamic properties, all of that along with the execution of the code and the simulations, that goes into the case folder. So first we will go to the solver folder. Here you see all these files. So all you have to do is just wclean and wmake. So this should compile the solver. These are some warning. No need to worry about it. Some convention, C++ convention difference might be there. Okay. So this has compiled, and you can see the last line. It created an executable face field which went into this particular location. Okay, and this was the location which I already showed you. ls, this location can be accessed using okay. So you can see that it has created the face field executable. So this compilation of the solver has to be done just once. And if you're not making any changes in the solver, that executable can just sit in that location, and every time you want to run a case, you can just directly move to the cases. So first we'll look at dendrite simulation. LZN 9B. So one thing we might need to do is, see, if I run this all clean, it is not auto completing and it says permission denied. And here also you can see that in my computer, all clean is in white color while all run is in green color. So green color files here are the executable files. So right now we don't have the execution permission for the all run file. So sorry, for the all clean file. Okay. Here you can see that X is the execution permission which is there for this particular file. Which is not there for the all clean file. So first time when you download the repository, by default, it will not be executable. So you'll have to make those files executable. So you can do chmod plus X all clean, and then same thing you can do for all run. Okay, and you can check now. Okay, here you can see that it has become X is also appearing, so it has become executable. So now I can run all clean. So what all clean does is, whatever, if you have previously run any particular simulation in that folder, for example, I have done that, because of which you are seeing these 3 log files as well as you are seeing the processor files. So I want to start fresh. So I'll clean it. Now if you see, those log files are gone and the processor files are also gone. Now, okay, so one addition, that you can use the infile generator, which is there, to generate the infiles for the OpenFOAM. I think I'll go through that once I'll show. So, So I've opened new terminal. I've activated the Conda environment, and so that then I have to go back and use Python 3 sim.py. Okay, so here I can go to. So as of now, we already have the infile. So I'll go to infile, and you can go to GP OpenFOAM. Choose infile, grand potential OpenFOAM cases. So right now we are doing simulation for dendrite nickel niobium. So I'll go here, and so already thermodynamic, infile is already there. So we can just import it. So it's a 200 cross 200 mesh, delta T, delta X. Rest of the things are already covered. So I'll just run this for, let's say, 20,000 steps.
So one of the things in OpenFOAM will be, as you will see, the delta T that you can choose here in this box.
Yeah.
This box that will allow you to
Yeah.
choose a delta T. This delta T will be much larger than typical explicit solvers. And that's the advantage we borrow from using an OpenFOAM environment. But I mean, per iteration, the OpenFOAM will be slower. But you actually get more work done because the delta T is larger because of the explicit.
So you can enter number of workers. So I can run it on 4 cores. So number of workers 4, and we'll just ignore these things, and we'll just go to domain filling, import shape. So, and I'm importing filling.in file. Import. You can see cylinder is imported. Next, again choose this. So these are the model specific parameter. I think so. Right now, this yeah. So these are not there, but if you want to generate the file, so there is some more editing that is required here. Just enter something. This will not be used in the simulation, so that's why you can enter some value here. And just come to this step and then generate the in file. So let's say in file input test and filling test.in, and I can generate the in files. And you should save those in files in the same folder. So by default, it will automatically open because I took the in files from the dendrite NINB. It is asking me to save it there. So I'll just choose it.
I think the
And
DNB
it's,
is something.
yeah, no. So I'll tell them. So currently this run is not working for OpenFOAM solvers. So, but you can generate the in files. Now we'll again go back. Yeah, better issue. Okay, so I created this filling test.in file, which has this fill cylinder and the input test file. So this looks very similar to the in files that we had previously for the other solvers. Now, if you are generating this in files by yourself, then there is just one thing that you need to change in the all run. In the future, we'll automate this, but as of now, if you have generated a new in file, then you have to go to all run. Okay. And here. So, okay, here I can't increase the font size. Okay, so in this particular line, you need to specify the input file that you have generated. So I think in Amrex also we have to do a similar step. So filling.in and tdb new ninb.in. So since I already have those folders, I'll use the existing ones itself. So I'm not changing it here. So now next thing is you just need to run this all run script. So it's a script file. If you run this, you can see that running block mesh. So this block mesh will generate the mesh for your domain. Whatever domain size and dx that you had specified, it will based on that it will generate a mesh. Then this particular step, it is filling in the temperature. So we are giving some undercooling to the system that is being specified here, and I think that is manually specified in the constant, right? Temperature, undercooling temperature.
Yes.
Yes, right. So and then decompose is we wanted to decompose into 4 processors, so which is done here, and running phase filled in parallel using 4 processors. It's showing. Okay, so it's running. It's not, so we can check the log in another terminal. So as you can see, it has created 4 processor folder, processor 0, 1, 2, 3, and it has created this log files for block mesh for the decomposed paradigm. Okay. So if you open this file, you can see that we had specified the dx, dy, dz as 3 minus 8, and these are the total number of points in the mesh. And we had specified the size x, y, z, 200, 200, 200. So that should be visible somewhere. Okay, yeah, I mean 200 cube, that would be 80,000 something. And similarly, you should not have any errors in any of these files. So you can see that fill transfer, if you see that end is written in this log file, that means it has executed properly and it has distributed the proper cells into 4 processors that we specified.
So OpenFOAM comes with its own parallelization strategy. So there is something called simple, there's something called Scotch. So in the simple strategy, you essentially do something like a block parallelization, like we saw in the morning. You split up into blocks of sizes, depending on how many workers you allocate. It's there in the decomposed part field text file. And that will essentially select the number of sizes or size elements per worker.
So there's a file in the system decomposed paradigm in the system folder. So you see the system folder here. So I'll just open the decomposed paradigm file. So this is where we specify the number of subdomains that we want to divide into. So we have specified 4 cores, and we are using a simple method. That means we are specifying. So since it's a 2D problem, we are decomposing in x and y direction in 2 parts. So the multiplication of these 3 numbers should come out to be the number of subdomains. So this is x, y, and then z. If you use the Scotch method, you don't have to specify any of these things. You just need to specify the subdomains, and OpenFOAM will automatically try to discretize such that you get minimum number of faces. So this is one change, one place where you would have to make the change. How many number of cores you want to run the case on, that has to be specified in this particular file. So we'll check what happened to our simulation. So as you can see, it's running. Okay. So while it is running, we can check how many files it has written. So I'm just checking in the processor folder. So these files, these are the time files. So 0th file is, we are giving the initial condition to the system at 0th time. What are the conditions? So this is specified by us, and it is already there in the case folder. the subsequent files are generated from the simulation. So we can view what is happening with our simulation. You just need to use paraview and facefield.foam. Enter. Here you need to choose decompose. So there are two ways of visualizing the data, or in terms of the file as well as in terms of the GUI visualization. Right now what you saw was we had 4 processor folder, and in every processor folder you'll have these many time files. So a processor, if it solves for a particular region, it will write all the data related to that region in this particular processor folder. So what I can do is I can run a command reconstruct, which I'll show you.
This reconstruct is the same reconstruct that Saurabh was using for the GP solvers that you were seeing in the model, or the KKS solvers. So essentially, it puts together all the data into one file. This is if you do not use the H5 formulation. In the H5, you write one single file. In the VTK things, you use this.
So I can use the reconstruct part, and what it is doing now is it is generating one single file. So I'll show you. So as you can see, this time files were not there previously. So now all those files which were time files which were there in each of the processor folders, they have all been clubbed together, and you'll file one single file for the whole domain for a particular time. Now since we have this data as well, so suppose if you don't do reconstruct, then you need to choose decompose case here, and then click apply. And then we can choose our phi is our face field order parameter. So here you can see that we started with a small nuclei at the end, at the corner, which is shown in the red color, and the blue color is the liquid. And you can see you get a nice dendrite growth. So if you keep running it for longer time, you'll see nice dendrite growing here. And this particular simulation I'm just running on my laptop, so this can be very well tested on your laptops also. Now since we have reconstructed things also, I'll go to reconstruct and then apply. So this also gives the same thing. So you can choose any of the ways. Then this is our chemical potential field. And you can see because of the difference in the chemical potentials, that is acting as the driving force for the growth of the dendrite. Okay. So in this particular simulation, we are not solving for a theta field because we have just one particular grain. Okay. So we will. So that simulation is still running. So I'll just stop that simulation. Control C. Okay. And
so Control C or Control Z will kill the simulation.
So now we'll move on to another simulation. Aluminum zinc. Okay, in that particular simulation, we had just given one undercooling, nucleated one seed, and we just let it grow. In this particular simulation, we will be giving cooling rate. So it's like a casting simulation. You are extracting heat out of the system, and we will nucleate based on what is the undercooling at a particular place. So based on the nucleation probability, some nucleus will form. If some nuclei form, and if the temperature grows higher in that region, you'll also see that those small nucleus will dissolve also. So that we'll see in this particular simulation. So again, I'll do all clean. And so again, for this, we have already given the filling and the input files. So this simulation is also running. So now the process to run any of the cases is the same. You just do all clean, all run. That's it. So I have already run this simulation. As you can see, I have already run the simulation earlier, and we have all these time files. So again, decomposed case, apply, then choose a phi field. See, there was a nucleoform there, but the temperature was too high, so it is dissolving. So the conditions were not conducive for its growth. You can see some nucleation happening.
The one next to the small, larger particle that disappeared because the heat was being there was heat evolution near the larger particle, so the smaller one disappeared. This is typical of what you see in Oswald ripening. This is what happens, right? You are near a, in this case it's heat, in the other case it will be mass. Okay?
So this particular, just observe this particular grain, it will dissolve. Okay. So in all of these simulations, we have incorporated four-fold anisotropy. So that's why you see a little bit of it's forming like a cube diamond. So this was for a binary system. We'll go to ternary system. So since the process is same for all the cases, you just have to do all clean and all run, and you just have to make sure that the all run and all clean files are executable. That's it. So that's why I'll just walk you through. So I have already run these simulations. I'll just show you the plots, how they are evolving.
Yeah, for this particular solver, there are a lot of examples. You just keep going into each of these folders. Just do all run, all clean. They will generally run. So there's no problem.
And all of this setup has been done such that it can run on your laptops. So except for the 3D simulations, you try any of the 2D simulations in the phase field solver, they'll all run on your laptops. So again, apply. So now this is a ternary system. So since it's a ternary system, you'll have two mu's. This is mu1 and mu2. Here, so again, in this particular simulation, we are not solving for theta. We are considering that the theta is same for all of these grains that are nucleating. So this ternary simulations will take slightly more time because you saw there are some. So instead of solving just one mu equation, here we have to solve for two mu equations. So the computation increases. So this will be little slower than the binary simulation. So I have ran it only until this particular stage here. Next we'll go to a multi-grain simulation where we nucleate multiple grains with different orientation and see how the evolution happens. So there's some nucleation has happened, and we can check the theta field. Okay, for some reason, okay, this is appearing very small, but these different colors that you see, those are the seeds with different orientations. Here you can see some nice dendrite growth. I mean, almost there. Okay. And same, you'll have mu fields. So it's a binary system here. So you have only mu1 value, mu2 is just blank here. And this thing that you see, these will come in the precipitations. So some fields which you don't see any values on the plots, those are just there. Those are meant for some different cases. And after seeing, we see this course. So beyond this point, we just see coarsening happening here. So they're trying to minimize their surface energy, trying to become all circular. So the model is able to do this as well. Then we have last case. So here I think. So here we are starting with 2 seeds. So this model is a precipitation model which also incorporates the elasticity effects. So because of which you'll see how the 2 nuclei which are next to each other, how they are going to evolve now. Okay. So you want to comment on this?
No. Elasticity was all right.
Yeah. So I think these are all the different possibilities that you can simulate using the OpenFOAM solvers.
So the same filling functions that you saw in the other solvers are also applicable here. So you can fill cylinder, fill cube, all this is filling functions that you have can be used here as well. So you can initialize microstructures in the same way that you use in other solvers. And the infiles are also similar. So the same infile, you just put it here. You just need to change that script dot read input. That script has to be changed to change the infile names when you want to run them. And in some sense, then you can just utilize the same case files. Just this line has to be modified. Okay. So
Okay.
OpenFOAM is pretty powerful, particularly because it comes packaged with very strong implicit solvers. So it's a good idea to. I mean, they were being used by the CFD community, so we tried to leverage that ability into phase field solvers, and it does happen and it can be used.
Okay. Any?
No, that's it. I mean, as long as you can write a P, huh? No, that's just the empty file. Yeah. If you need a foam.foam file to basically because when you ParaView write something into it when they initialize, and then it deletes it.
So it's a 0 KB file, facefile.form. So it just need a .form file so that during runtime, ParaView can do. No. So these are only the case files. The solver sits separately. So if you see here, the solver sits here.
So in
This is
this,
the
the
solver.
main thing is you will have several .h files that you write down, and those .h files are nothing. They are essentially equations. So this has a way that you can initialize equations, and that equation just has operators, and operators have very nice names. You can just write down an operator for Laplacian, and it will calculate Laplacian for you. So you can show one instance of it.
Yeah.
Maybe
So
not. This is already too complex. Maybe just
no, here itself, if you go down,
the theta or alpha equation. Alpha equation.
Yeah, I went there only. So you have to go down.
Okay. So if you just see this alpha equation, it's readable by a human. So omega epsilon FEM dt is just d dt, is derivative d phi by dt. So this is how that is on the left hand side. Equal to signifies it's an equation. On the right hand side, this is just the evolution equation. 2 epsilon gamma FEM Laplacian. FEM Laplacian is a Laplacian of the field that is inside. So this is how you write down an equation. Okay, direct type.
Yeah. So it takes care of all.
Right, that's. But this is header. This is just a header, and you just need to include this in the main file #include.h.
Yeah.
I mean, I mean, you can initialize, but your growth will not be determined by your initial shape. The growth will be determined by the anisotropy function that you have. And the anisotropy function that is coded presently is giving you diamond or any rotation of the diamond, only that. We haven't coded in sixfold or anything into that as yet. They will come back as future releases. So typically in material systems, you get fourfold, sixfold. This is the two typical ones. So we will code in the sixfold one soon. There you need higher. We will be coding in for 3D shapes, for example, where quasi-crystal shapes might be relevant. So these anisotropy functions can be keep adding in. So as and when they are there, we will just put it in. As when if somebody is really interested, we can also tell you how to do it. You can.
Any questions? The audience. Okay, OpenFOAM solver installation PDF not provided. Oh, it's already there.
This is there.
Yeah, this is there. Okay, wait, I'll just share this link again. So can you check now whether this file is working?
Robinda.
Okay. So you can get back to us if you have any questions about the solver or about MicroSim installation. Any of the solvers, you can contact the respective teams also, or you can just email us on nsmmicrosim@gmail.com, from where you are receiving all the emails. So I have updated this drive folder just in case if you are not if you were not able to find this, you can go back again to that folder. Morning I had shared the link. You can go back to the folder and download the instructions. So these instructions are also available on repository as well. So you can go to Grand Potential OpenFOAM and open the README. So those instructions are here as well. Yeah. Oh, wait, sorry. Shit.
Sharing.
It was not sharing previously. Yeah, so as I was saying, you can go to our GitHub repository, MicroSim, go to Grand Potential OpenFOAM, open the README file. So those set of instructions are available here as well. You can access them from here. Okay. Okay, thank you. It is working. Cool. Any other questions? I guess not. I think then we can conclude.
Yes. Okay, so we come to the end of the session as well as the two-day workshop. So thank you everyone physically and also people who have attended online. I think it was the interactive sessions were nice because we got important feedback for our stuff, and as well I hope you got something useful out of it so that you can take back and utilize at your workplaces. So thanks again for coming and being part of this activity, and we will have this regularly every year around this time. So hope to see you next time as well. With that, we can close, and thanks everyone again.
Thank you, everyone. Okay, good show, Sabril. Oh, yeah. Thank you, sir. Yeah, congratulations to all the developers and thank you all the participants.
Yes, I think the developers put up a very, very strong, a very, very important effort, particularly the solvers which came new this time. They were very strong development. So please keep out the good work so that we can have a stronger release next time. Great.
Okay, thank you, people. So we'll be ending. I'll be ending the meeting now.
Yeah. So the wait. So the recordings of all of them will be uploaded on the YouTube site. That will be also accessible from our website. Yeah. So you can access these videos again and be able to go through them and try out when you have the information. Also, the slides from all of our people who presented will also be there on the GitHub repository, so you can access the information there also.
So in the coming week, we will update all of these things, the repository with the documents, presentations, and as well as the YouTube channel. So if you go to our website, you can click here, YouTube channel, click here,